Okay, so it is our pleasure to welcome you again to our Astronomy Colloquium today. And one of the small announcements for our next time, we'll have the Christmas Colloquium. So after the Christmas Colloquium, we'll have a little small get-together in case you want to stay around. But that's next week. But this week is my great pleasure to actually introduce Shri Kulkarni, and he's from Caltech, and he's one of these very famous astronomers for kind of everything. So in case you wanted to know who worked on the discovery of the first brown dwarf ever, or the first millisecond pulsar, or who figured out that gamma rays are actually outside or extragalactic, so outside of our galaxy, that would be him. So if you have any questions for anything else, the question and answer period should serve this time. And one of the other things is interesting that he stayed at Caltech for all of his career, basically. And he's the MacArthur professor at Caltech right now, and he had visiting professorships in, the who of universities across the United States, whether you say Berkeley, MIT, Harvard, whatever you want. And today he's going to give us a good insight into everything that happens in the universe. Would that be a good description? And so, we welcome Shri today.
Okay, so I wanted to tell you about the dynamic optical sky today. It's something I've been focusing for the last 6 years or so. Before I go into the main talk, I want to spend about 10 minutes or a little less telling you something actually I think which is more interesting than the main topic itself, but may not be so obvious. Okay, it may not be so obvious. Nonetheless, I think it's important to talk because I think that many changes happening in our subject, and those changes in my mind are far more profound and far more important than the special topic that we all work on. Okay, so let me start off with a combination of assertions and facts. Okay, and that's the first part. So I will make some assertions. One is that subjects which are phenomenological in spirit are driven almost entirely by technological progress. So what do I mean by subjects which are primarily phenomenological? Many of us like to think astronomy as an application of physics to the sky, which is pretty good. I mean, that's what we do a good fraction of the time. But that's a somewhat limited view, actually. It's in fact a subset of what we do. The point of an astronomer, or a biologist for that matter, or a geologist, is to explore the world, the universe, the plant, animal kingdom that we see around us. Okay? So exploration is a very big part of these subjects. And in contrast, perhaps the most successful subject of all of our scientific endeavors, other than mathematics, for which I have the greatest respect. But next only to mathematics is physics, where physics is about distilling many things we see into simplifying views. So the idea of physics is one of reducing complex into some principles. And it's been very successful. It's hard to deny the success of physics in the last several hundred years. It's been so successful that many scientists, and recently, unfortunately, many astronomers think that's the way to go. And as I said, applying physics to the sky is just one part of the activities we do. The point of an astronomer is to go and discover the universe as it is. There is no simple theory or a single theory for the formation of the solar system. Okay, the solar system has many accidental features. They're not very important, but they're very important if you live in this solar system. And our job is to then go and look, understand planet formation in a broad way, and then specifically apply to the solar system or other solar systems we may end up finding. So I hope you understand that subjects which are phenomenological really require observations and really require measurements. They can never be figured out purely by mental process. Perhaps the greatest astronomer, physicist we had in the last 100 years or so is Eddington. And even Eddington did not understand, when presented with the data or the observations of Sirius B, which is a white dwarf, he didn't understand. He knew enough quantum mechanics, his general relativity, astronomy, and he could not understand. So I really wish that some of my senior colleagues, especially those who seem to have now become self-styled astrophysicists, actually understand this very important distinction between astronomy and physics. Okay, so my claim is that in subjects like astronomy and biology, they're in a fantastic growth phase, both of these subjects. And they'll continue to be rich into the next decade. I don't know about 2 decades from now. My research horizon is usually about 5 years. After that, it's very hard for me to see anything. And if you believe step, my first assertion, and the second one is I simply state as a fact. You open up any newspaper, you hardly like to see an article on condensed matter or atomic molecular physics. You will see either a cure for some disease or a big astronomical finding, almost on a weekly basis. Okay? If you believe these first and second lead you to a third conclusion, which is that greatest progress happens in those areas of astronomy where you have really great technical progress, or where
progress just data volume, or at some point the field becomes so empirical and there's no understanding.
Absolutely. In fact, that is the state that biology went through for a very long time until essentially molecular biology changed that from one where basically of classification to deep understanding. We haven't yet reached that point in astronomy, in my opinion. Okay. So anyway, so this, so for me, this has been a very important thing. For me, doing research has been to identify those areas where the change is going to be the largest, and then to go and work in these areas, because then you don't have to be very bright. You just have to be there, and discoveries just come to you. Okay, they really come to you. Okay, so let me finish this little prelude with 2 architectural beauties. One which represents the old world. It represents the leaders and all the old things and all the bad things in the field. And the other architecture represents, I think, the exciting future, which I hope the young people will appreciate. So this is a classic picture. It's hard to deny the beauty of the pyramid, if you especially think of the engineering feat when it was done. But this is the old world, and this is the old style of doing astronomy. Where you build small telescopes, and you build bigger, and then even bigger, and then even bigger. And you know, just for those of you who don't read history, each one of these empires which try to build bigger and bigger buildings actually collapse due to the fact they spent money trying to finish the building. It's useful to know. Okay. In contrast, I think this is a very nice building. It's beautiful. I think I actually appreciate this building better, but probably I'd like to really live in this building. So there are inversions that can happen in the course of subjects, and I think we're on the verge of an inversion where there will be some groups, some countries, which will go along the way of the pyramid, and those of you who are clever will do the opposite. Okay, so I want to now demonstrate this conclusion with an actual project. Okay, so now I'll demonstrate this building with an actual project. Okay? So the topic is about supernovae or cosmic explosions, And here's an aerial view of the Palomar Observatory, of which I'm the director. And this shows, of course, the famous 200-inch telescope, which saw first light in 1949. And this is the 48-inch Schmidt telescope, which basically undertook the first systematic, fairly deep optical images and catalog of the northern sky, and commissioned in 1951. This is the 60-inch telescope commissioned in about early 70s to help students train on that telescope before they used the big telescope. But our story really starts off with this telescope, which is the earliest telescope that came on the site, about 1936 or so. And this is the 18-inch Schmidt telescope. And the Schmidt telescope was a major technical breakthrough. The so-called Schmidt camera was invented by German optician Bernhard Schmidt. And when Fritz Zwicky, who was the very first astronomer to be hired at Caltech, understood the value of this design. And this design basically allows you to couple a very large field imager behind a large telescope. Okay, you can always come up with an optic which is lenses, but they don't have large collecting area. Okay, for the same field of view. So Zwicky got some money from his wife's family, and commissioned, and he working with Barde, they began observations with this 18-inch Schmidt. So here's Zwicky with the 18-inch Schmidt. Well, this is the very first application of the Schmidt design for astronomy. Zwicky was a very amazing guy. He really was a polymath. He had fundamental patents in jet engines, philosopher, a theorist, experimentalist. And the part I'm most impressed with is that he actually observed, he stayed through the nights, he took the data, there's still his logbook where he keeps the entries of his things. He took photographic plates, developed the plates, blinked them, so he put two plates, one taken yesterday or today, and you compare the two. It's very laborious. And then he wrote the papers. Okay. You know, it's easy for professors like me to do research because we don't actually do much work. You know, this is a real scholarship in my mind. But anyway, it's only possible for a few people. I think most of us would have. So I have a simple unit of measuring people I know. I always measure them in Zwicky units. And most of the people I come across are micro Zwickies, but once in a while I come across a mini Zwicky. Okay, so what Zwicky introduced a concept of phase space for astronomical phenomena, and we use that today. He had a different word, he didn't call it phase space, but we use that even today. And the idea is, here it shows the phase space for explosions. In a very famous paper, Barde and Zwicky distinguished that these transient objects, there are two types. What is initially called as nova stella or new stars, they realized there are two types. So what's shown here in this, which I'll simply call in honor of Zwicky, I'll simply call the Zwicky diagram, is the time scale of the phenomena. It may be the rise time or the decay time or the total lifetime. We'll not worry about the details. It's roughly the characteristic time scale in which the phenomenon lasts versus the peak luminosity. And here we'll just for consistency use the V band as the measurement band. And this is the absolute magnitude. And you can see that in this Barde and Zwicky paper, they realized that novae and supernovae, or this other object called supernovae, were much luminous compared to novae. And that's where they coined the term super-nova to indicate something which is maybe 10 to the 4 times brighter than the ordinary novae. Okay? So we'll keep coming back to this diagram because this project that my students and I started in about 2009 aims to explore this phase space in the true spirit of exploration. Okay, so let's focus today. There are all sorts of cosmic explosions. There's all sorts of time domain astronomy things which I have little time to talk about because that would be almost a whole course. We'll only talk about supernovae or some weird sort of novae that astronomers are now finding. Okay, for students in the audience, while what is the broader context of the supernova? Well, most of the supernova we see in the universe are actually deaths of massive stars. There are a small number of supernovae which come from weird channels, so so-called like type 1a supernovae, maybe some things coming from coalescence of white dwarfs, which we haven't yet given a name and so on. But the most common one, somewhere once a second in the universe, you'll find a massive star dies. Okay, it's a fairly frequent phenomenon, once a second. So here, for example, is M51. It's apparently very dear to Heidelberg because we even have a whole building for M51. Okay. So I hope you don't have too many supernovae going off in M51. Your building bill will be very high, but M51 seems to produce a supernova about every 10 years. In contrast, our own galaxy maybe every 100 years or maybe a couple of 100 years. Okay. So a massive star dies, shows up here, and the reason a supernova is interesting in a broader context is when the universe began, it was very simple in many, many ways. The universe was extremely homogeneous. The density of baryons or matter and energy in any form, including photons, neutrinos, gravitational waves, in one part of the universe was the same density in another part of the universe to one part in a million. That's an amazing degree of homogeneity. It is also very simple. There's only hydrogen and helium. Okay, there are no other metals. So, in fact, so much so that most astronomers instinctively call anything other than hydrogen and helium as metals, which of course would shock any real chemist because we know that lithium is not a metal and so on. But the chemistry at the beginning of the universe was simple: hydrogen, helium, and this is all missing. Thanks to supernovae, the periodic table got slowly populated, okay, to what we see now. Okay, so if you want to understand the growth of elements in the universe, from the simple universe it began to the current universe with the metals that abound here, of the order of 1 to 2%, which then made other things, like minor things like planet formation, life, all this stuff possible, then you must appreciate the important role of supernovae. Okay, there are a few other motivations to study cosmic explosions, and they have to do with new fields in astronomy. So the first one I'd like to draw your attention is energetic particles. Cosmic rays were a major part of physics for a long time, but recently they're coming back again. The physicists have discovered ultra-high energy cosmic rays. These are cosmic rays with energy of 10 to the 21 electron volts. Now, if I just quote you a number with many zeros, it's not very useful because you must always place any measurement you see or anything you hear in context. Otherwise, they're just one followed by any number of zeros. 10 to the 21 electron volt would be the fastest ball ever thrown by a human being. It so happens the fastest ball is a cricket ball. And you do half mv square for a standard cricket ball and put v as the highest velocity in Google search. You'll find it's approximately 10 to the 21 electron volts. Okay. Well, that should impress you because in a cricket ball there are lots of nuclei, there are lots of protons. In contrast, this energy is occupied is due to just one proton, and perhaps in some cases an ion nucleus. Okay, so the origin of these is something being probed by Palomar Observatory, for instance. Similarly, very high energy particles from in neutrinos by the Ice Cube project in the South Pole. Now, as these high energy particles come towards you, 10 to the 21 electron volt, okay, some very interesting things happen. Let's assume for the moment that this particle is a proton. Now, you know the rest mass of a proton is 1 GeV. And therefore, the Lorentz factor of this 10 to the 21 electron volt proton is 10 to the 12. What does this 10 to the 12 Lorentz factor particle see? It sees in intergalactic space 400 photons per cubic centimeter from the cosmic background radiation. The average energy, 2.7 kT of this black body radiation, is about a few MeV, milli-electron volts. So now, if you just did simple inverse quantum scattering, you would get gamma squared, which would blow away the entire energy budget, except there are many new channels which open up at such high energies, including the production of pions with an energy, rest mass energy of 200 MeV. And this is called a famous effect, it's called the GZK effect. So as a very energetic particle comes towards you, it actually loses energy due to scattering of CMB photons. So the origin of these particles is necessarily nearby. There may be high energy cosmic rays at z equals 10. They don't come to us. The only volume for people studying this of value is about 100 megaparsecs. Okay? Next, here's a simulation. I think it's by Rupert and Bianca of black hole. It's schematically shown here. The neutron star, the simulation start off where the tidal forces are strong enough to start ripping off the neutron star. Only 1 millisecond has gone by the way, so far. Matter rains down, forms in this black hole, jets come out, and we think this is a plausible model for short hard gamma ray bursts. But in the process of spiraling down, before it gets to that tidal disruption, gravitational waves will be generated, and it's the goal of LIGO and Virgo projects shown here to detect these small gravitational perturbations. Now, gravitational waves are very transparent to the whole universe, except the sensitivity, the instrumental sensitivity is such that initially, for the next 5 years, into this decade, we'll probably be lucky if we go to 100 to 200 megaparsecs. Okay? So there are these two fields which are, I would say, very exciting, and for them, the high redshift universe doesn't matter. Okay? And for me, I'm a sort of a guy, I really like close things very well. I like the solar system. The next thing, I like the galaxy. After that, like M31. And if pushed, I can go to 100 megaparsecs. After that, I never find anything too interesting. Okay? And I never understand why people do these sort of very low resolution studies of very distant universe. Anyway, what is made of all sorts of people. There are a lot of Millie Zwickys and Michael Zwickys, so we've got to keep them busy too. Okay. I was looking at Fabian when I was saying all these things. Okay, now let me. To study these nearby universe with the goal of gravitational wave astronomy, ultra energy cosmic rays, and just to explore the Zwicky phase space, conceived of this project called the Palomar Transient Factory. And so let me describe, in what way was this somewhat novel, because there are many synoptic surveys, some of which your own groups here involved, such as PanSTARRS. Now we have SkyMapper, and there are other surveys like Dark Energy Survey, future surveys like LSST. The concept of this, the main thing in this project was not to sort of build huge things, is to actually take existing facilities and then focus very sharply on only one thing. And I always like automation. I'm one of these guys. Love going to automotive, museums. So I'd gone to give a colloquium in Munich, and of course, after giving the colloquium, one place worthwhile visiting in Munich. But there are two. One is the Hofbrauhaus, of course, but the other one is the BMW Museum. Okay, and that's it. After that, I went and took the plane back to LA. Anyway, so what we did was we took the 48-inch telescope and outfitted with a large mosaic CCD, and this job is simply to take a picture in one band. Okay, so in contrast to PanSTARRS or SDSS or DES, we take it in only one band, because on an average, if you take 10 such pictures amounting to 100 square degrees, you'll find only one supernovae or one transient or strong transient. So for our purpose, we don't care all these other pixels. I just want that one position, RA tech and time 0. And that is data is annals real time, sent to the 60-inch, where we then get the colors only for that one point. So this right here gives us a multiplex of 5 over all these existing surveys. So our throughput for transients is much larger than any existing survey, and will be so for quite some time. And from the colors we can decide, is this another 1A supernovae, is this another type 2, not very interesting, some contextual information, and if it's something worthwhile, we get a spectrum. So I hope you got that sense of a factory here, where we're sort of taking these telescopes and acting it as one unit. Okay, so some hardware. Here's the old CFH12K camera. Some of you may use this. We refurbished this, and one of the CCDs is dead. And that's for astronomers. These are the technical details. of our main imaging camera, and the moon has been just photoshopped in to give you a sense of the scale. And this is real live data. Okay, there's all sorts of galaxies, stars, blemishes, and problem pixels, and real signals. Okay, now the big change that's happened in our field, and I think most astronomers, even especially the older astronomers, actually don't understand at all, apart from the very big change I described to you in the early part. But on a somewhat minor scale, the big change that's happened is when people think of a project or something, they always say, oh, well, we think of capital cost. We need to build a telescope, so steel, glass, dome, road, and so on and so forth. You know, that's not true actually. For many of these projects, the real cost is not at all that. In PTF, the real cost of the project is not the capital cost, is not the running cost. It's something which I call as Gray-ware. Is actually to find really bright people to write some amazing pipelines. Okay? Because you can't call up some big companies like Microsoft or SAP to do this sort of work. And even if they did, they'll charge you so much that it'll be broke anyway. So this project drew strength from all these collaborators here. And the part that really makes or breaks this project is not just the pipelines, but the cleverness that goes into analyzing the data. Okay, that is a thing. Either if you start paying money, it in fact will dominate the cost of this project. So for PTF, capital cost plus running cost in the simple sense of the word is maybe $3 million. But the cost of actually making all the rest of the stuff happen is probably at least twice that. But fortunately, I'm somewhat clever about these things. I called all these young people and said, come and work with me, I'll make you famous. I used to say rich and famous, I no longer say rich and famous, I said I'll make you famous. So here's then young Josh Bloom, he was in charge of machine learning, because we use that a lot. From his experience, now Josh is a professor at Berkeley, he's in fact gone on to start a machine learning company offering some machine learning solutions to the commercial world, in addition to being an astronomer. Young Suresh was in charge of the pipeline, photometric pipeline. While Peter is not all that young, but he's the uber master of image difference in pipelines. Iran Ofek came to me as he had finished his PhD from Israel, and he came and he was in charge of sequencing, which I'll explain what it is in a minute. This is my engineer and our group, chief engineer Richard Duquesne. Robert Quimby had finished his PhD from Texas, and he was in charge of the software integration. It's perhaps the hardest job in this. Nick Lloyd finished his PhD from Cambridge, UK, and he was in charge of project scientists. So I have a very simple way of running a project. I had all these young people. My style is very simple. I don't meet students unnecessarily at all. In fact, I like to meet them once a year. I'll say, well, here's the project. Let's discuss that for whatever weeks you want. And we figure out what is the scope of the thing we want to do and how much of resource it takes. We argue, and after that it's over. They meet me a year later, and it's all done. And the key thing is to find bright people and not waste your time with micro Zwickys at all. Okay. And they've all done very well. They've all become professors or famous people somewhere. Okay, so this sort of project has in software, and even so much software that's just, to me, really amazing. In fact, in India, there's a company called Infosys. It's probably the second largest software provider, and one of their vice presidents, he had heard my talk at MIT, and he's asked me to come and give a talk on all the software things we're doing in this project, because he found it very impressive. So let's start off a little bit with the flowchart here, which is we observe that we take the data from the 48-inch. You have to sequence. Most people don't understand what robotic telescopes mean. The idea of a robotic telescope is you think, oh, well, it has a weather station, it figures out when to open and close and so on. That's the easy part. That doesn't take all that much effort to figure out. The hard part is how to make the telescope think on its own and observe so that you're not there running the system. Having a graduate student sit down and write a script what it should do every night, well, it may be fun for the first 3 weeks. But in the US, grad students, if they get really upset, they can go buy a gun. Okay. Generally, the professors are more protected. I have to worry much more about this. So this is all, and so there's great cleverness in writing the sequencing software actually. So this is self-sequenced. So if the weather is bad, the software heals itself, and eventually it goes out of kilter about a month later. Then you reset it and it starts again. So we actually have no one doing this. In fact, my biggest innovation has been that the main realization is two things. One is, if you really want to do great astronomy, you have to get the astronomers out of the observatory. Okay, because they only slow things down. It's so this has been a big philosophy. So we're trying to get to the point like a Toyota car factory. No one on the floor. Stuff goes in, cars come out with no one inside. That's like, I love it, Okay, so there's a lot of automation that's happening here with actually no human being in the loop. Okay, it's done the usual stuff, we get terabytes, petabytes, or whatever. So that's all pretty straightforward. I came to Europe over 2 weeks ago. I was in Italy, and I came here and I prepared this slide that the number of supernovae we went from 2009 to now is 2040. Before we started the survey, the entire global integral of supernovae, starting with S Andromeda, the first supernova discovered in modern times, 1855 or 1885 again, to now was about 4,000. Okay, of course now it's accelerated. So there's in our peak period we are finding 700 supernovae a year. Actually, we can easily find about 1,200. Okay, but not find. But these are not just things we discovered. We actually have classified them. We've got spectroscopy, so we know what they are. Not just stuff that came and went. It's no big deal to find supernovae. On a good night, we can find one every hour or so. Okay, so there's a huge amount of nice work you can do with demographies and so on and so forth. But then I realized when just preparing this talk, and I just went to our webpage where, like you have McDonald's hamburger served, we have a supernovae discovered and classified, NEOs found, comets found, and then it turns out it's already changed a little bit. Okay, so it's a very active program. So let's go to the Zwicky diagram. We start with the classical novae, the 1A supernovae. In some sense, they're very simple supernovae, and then the core collapse. These are the massive stars that they die, they produce in the end a neutron star black hole, or in some cases they may perhaps completely blow things away. So here it is. Here's the difference between an astronomer and a physicist. A physicist would have just thought, yeah, here's something, and they would not go around exploring. But if you start exploring, you find some very interesting things. So we have all sorts of new classes. I don't really have the time to go into, but I just want to give a flavor. We have supernovae, which apparently only produce a lot of calcium. And there's a recent paper, some authors have now speculated that these sorts of supernovae, in fact, may produce most of the calcium in the universe. That is, the calcium actually is predominantly produced in this calcium-rich supernova. Kind of interesting to think that the calcium in my teeth is produced by one kind of supernovae, whereas the iron in my blood is produced by a thermonuclear supernovae. Okay. Then we have things which I don't know what else to call other than saying luminous red nova. They're luminous because here's a nova sequence and they're 100 times brighter. They really are red. That is, if you viewed them with your eye, their peak, new FP will peak at 1 micron. Okay, and they're new, okay. And there are two kinds here. This brighter one, arguably is electron capture supernovae. It may happen in the range of 8 to 10 solar masses, and these may be common on evolution objects, or maybe it's a spiral of a exoplanet of a hot Jupiter into a parent star. Okay, they're very fast supernovae, which may be 0.1 explosions. No time to go through this. And then there's a whole class of luminous supernovae. These are supernovae that come from very bright stars. And the primary contribution of PTF was to recognize that this sort of luminous supernovae, there are two main branches. The one which was known before, involving a lot of hydrogen, but the ones that we, especially Robert Quimby's work, showed there's luminous supernovae which are 10 to 20 times brighter than 1A supernovae, last 10 to 20 times longer, and produce just far more energy, and like hydrogen. And we still don't really understand the origin of these objects.
Where do your sensitivity limits exclude regions from that diagram?
Pardon me?
Where does your sensitivity and time resolution limit exclude regions from that diagram?
That's a little harder. I'll come back to that a little bit later. Okay. So then there are also some other fun things we found. Some supernovae announced their death. about 40 days before dying. So here's the R band magnitude versus time for this particular supernova 10 TeL. Upper limits, some detection about 40 days before, then actual supernova. We know we have spectra here to actually show this is supernova. So the idea here is that some of these stars, in fact now so we went back and looked at a lot of our super type 2N supernovae, and most of them eject a huge amount of matter a few months before they actually explode. And then they explode. Then you say, wow, we see like Eta Carina has thrown 5 solar mass, what's the big deal? The big deal is, if we just did that randomly, it just put out some mass, 10,000 days later it exploded, it's fine. The big deal is, in fact, to explain this very short time scale. It's hard to explain such a short time scale between the core and the surface. It's obviously not photons, it has to involve some sort of nuclear instability that we haven't yet properly modeled. Okay, so after doing this sort of a broad survey where we looked at many supernovae, we went into low latency. So if you sort of look this as a process, we are trying to understand why is it that we take an additional day to do the spectral classification. So the Japanese have a word for this, it's called Kaizen. Kaizen is a manufacturing term invented by Toyota, where if you want to improve a process, you improve the process not in a dramatic way, which would be the American way, which is the largest order of magnitude, but you actually look at the process and say, I'll change everything by 1% for 1 month. Next day, everything by 1%, okay? And then over time, so we Kaizened our way through it. It took us a year to go from getting the CCD images or photon hitting the CCD to getting the spectrum the same night. And we are lucky because nature blessed us with a 1A supernova in Messier 101, the Pinwheel galaxy. And so it's a very nearby 1A galaxy, and we found a 1A supernova only 10 hours after it exploded. So there are all sorts of fun things you could say. We could actually limit the size of the exploding star. We could say what is the nature of the circumstellar medium. And the nice thing about this is with one observation, we got 2 different nature papers. So, highly efficient observing here. Okay, so we have now made this. We recently have found likely a Wolf-Rayet progenitor for 1B supernova, which would be a very nice confirmation of some theoretical ideas. Okay, so moving on, here's the exposure map. The difference between what we are doing and other surveys is we do high cadence observations. We visit some parts of the sky very frequently because that's our job. So this tells you this means we visited 7,396 times. That's very few fields actually. Typically we visit them several hundreds of times. Okay, we avoided the galactic plane until last year because we didn't have the ability to process this. So we've done all sorts of very interesting other things which are now, so the supernova part is actually the easiest thing to do, and that's the reason I wanted to focus first on that. Because if you want to do supernova, you don't have to have very high quality data reduction. All you need to know is nothing here yesterday, something here today. But if you want to do photometry, then every one of those observations should be linked to the same basis, and that takes a lot of effort. So, but finally, we are in a position to actually do this sort of photometry. And so we've done all sorts of things which I won't go into. Branimir Cesar, who's just come through Heidelberg, he looked for other lighting out the galactic halo. Sumin Tang, she's found the first sample of our Corvo stars in another galaxy in M31. Group at IPAD found a young transiting planet in Orion. We have this nice project in Orion where we just sat on the Orion star cluster for 40 nights. And another group is looking at gyrochronology, which is aging the star, or getting that age of stars through rotation. I meant here to say AM camera, not RS cameras. Even though our galactic exploration is small, we already found new FU Ori stars, and then all sorts of fun things of Novi in M31. Okay, so what's next? And so I hope I've convinced you that you don't actually always have to build a $1 billion mission. It's easy to think of big missions. In fact, if you go to my webpage, you'll have I think it's a correct observation. It asks a rhetorical question. So why astronomers like to build big telescopes? And the answer is, because given a sufficiently large telescope, even a sufficiently idiotic astronomer can make a sufficiently great discovery. Okay. The challenge is how to do it the other way around. Okay. So I hope I convinced you by using old telescopes with a little bit of some thinking and some very clever young people, you actually can be doing some very interesting astronomy. We are writing a paper every 3 weeks. I know we have about 4 or 5 papers in Nature and a similar number in Science. And the rate of writing papers is simply limited by how much time we have rather than the data. Okay. So yeah, you can always go to a big telescope and write a paper. I think if you want to be clever and you want to be a real astronomer, I think you should try to do the other way around. Okay, so let's say what next? So this question Joe asked, we are roughly exploring the phase space of 1 to 100 days. That's our phase space. And we only look at, like classical moon, we only in M31. Okay, we won't find this outside, that's our limit. Then as you go to about 100 megaparsecs, we are somewhere in this region. Okay, so there's this whole phase space left here, below 1 day. So that's what we are focusing on in a new project which we call as IPTF. And we already have found, in fact, our ability to, this is somewhat detailed, but we have found perhaps a new type of a cosmological relativistic transient, or it could be, there's a possibility it is for PTF11 EGG. And then we've been able to look, purely optically find, go from 100 square degrees of error box to the actual 1 arc second. Well, this is actually, I had to say, it's a real technological feat. This is non-trivial. If you're not interested in these sorts of technical feats, you may not be impressed. But to go from 100 square degrees, needle in the haystack, and all done in 4 hours, this is, I think, really, I'm very proud of it. And this is actually a dry run we are doing for the LIGO. When LIGO turns on, we want to be in a position where we can actually go and do localization of the electromagnetic transits, and we're actually doing surprisingly well. So let me end by talking a bit about what I sort of see as the next phase for this project. And while if I said all these wonderful things about Zwicky, he's the first one who figured out dark matter, strong lensing, neutron star, origin of cosmic rays, fundamental patterns on jet engines. So you would think he'd be named. We'd have a facility, okay, like another space telescope. But Zwicky was also a bit of a guy who was somewhat impatient. He was a bright person, a super bright person. I probably found other people somewhat tedious. So he never was popular. So I thought, okay, no one's going to name anything after Zwicky. I'm going to do it. So we'll call this a Zwicky Transit Facility. We're going to increase the field of view from 8 square degrees to about 47 square degrees with these new 8-inch wafer CCDs. We have built and commissioned already a robotic spectrograph, because right now the way astronomers do spectroscopy is, it takes about 2 people, you look at the acquisition field, you argue with someone, it's not up and down, and then after about 3 minutes you put the star in. But we are now built this very low resolution IFE spectrograph with no moving parts, calibration very much in mind. And it's commissioned now, so we can just do robotic spectroscopy. Discover, identify spectra, 30 minutes later we're done. We also want to do light curves and figure out whether these are happening in the cores of whether the nuclear events or supernovae close to the nucleus. So we built robotic AO. So I don't know if any of you guys have done AO observations. Usually it's like launching a space mission. There's one guy, laser scientist, yes, ready to go. Deformable mirror, yes, ready to go, and so on. So then finally say, okay, let's turn on the switch. Okay, so maybe if you get a dozen things done, you're like a big hero. Wow, we're way beyond that. We do 250 targets a night. There's no one in the building. And as I told you, get the astronomers out of the building, science goes up. So here's a picture, here's a still movie. So this is our robotic AO system. This is a 20-watt ultraviolet laser, JDS Uniphase 355 nanometers laser. And we're using the Rayleigh scattering. It's range gated to about 10 kilometers, or about half a kilometer at that radius. And you can see, even though the picture, people taking the picture outside the building, I told them they can't go inside the building for the whole night, just to make the point it's recording. It's fun. So we've been doing some really fun cell astronomy projects. We say, oh, let's look at the multiplicity of G stars. You know, in 4 nights of observing, you can get 1,000 stars, and then you can write a little paper. Okay. Okay. Anyway, I'm assembling the Gray-ware for the next group. Unfortunately, a couple of them escaped me already. Branny is come to Heidelberg. This guy got so bright from Microsoft Research hiding right away as soon as he finished, but there'll be other young people. So I hope I've given you a somewhat contrary view of astronomy that doesn't require billions of dollars, which I think you can do some very interesting things. And if you don't do such things and instead focus all of our energy and most of our money on rather big things, then astronomy will become as boring as a high-energy physics is today. Thank you very much.
Thanks for a great talk, and as always, students first.
Okay, so DTF and ZTF can definitely do like high cadence observations. We are in a way, ZTF is maybe limited by the fact that there are plenty of rocks out there flying. So unless you want to get spectroscopy of a lot of objects, you need to wait for about half an hour, 40 minutes, so that the thing moves.
Yeah.
So that represents a sort of, not a true floor, but a practical floor to how fast you can do follow-up spectroscopy. Okay.
Yeah, I agree with you. Yeah, that's reasonable. I mean, there are technical ways to overcome that. If I had the money, I'd build another 48-inch or another camera, maybe 200 kilometers away, use local parallax, eliminate it. So, that's why our limit is about half hour to 1 hour. It's not any faster.
No, to university.
Does the ZTF also respond to the alerts and also
Yeah, so the question, if I understood right, is do we respond to GRB alerts? We don't respond to GRB alerts which are found by Swift or something because, it's not necessary. The positions are already very good. But these two are actually PTF response to GBM bursts on Fermi. And this required a search of 72 square degrees. I don't know, okay, 72 square, I don't have a picture, but 72 square degrees of search to locate this object. Okay, so we are now in a position where we can actually go after literally 100 square degrees. And the second one this was about 100 square degrees. This redshift was very small, this is about 1.6.
Yeah, your part, 50% of sources that was unclassified. You didn't have yet time to classify them, or that there's some weird features?
No. There's enough time. That's what you do astronomy for. They're not obvious. One is 1 BC or 2, and those are the ones that keep us busy.
But is something that has similar spectra to each other? Or?
Yeah, so some of them have now come into this sort of, so initially this is a calcium bridge, so we have maybe about half a dozen of those, so they're slowly falling into a pattern.
Okay, so it's kind of a different category by itself.
There are many different categories in that.
Oh, okay.
3% of 2,000, okay, is 120. So there are still a few which we haven't yet figured out.
Do you have any other questions by students or postdocs? Okay, then I'll open it to the younger part. Sure.
So for those of us that care about things further away than urban parsecs, you didn't say much about orbit afterglows.
Yeah.
And I was just wondering, what is your sensitivity to those? And, it would be great to find a GRB that's very luminous going on, so it's to get a very high quality spectrum of something like this universe, etc.
Okay, so this object that I was taught briefly, it's either this object, we don't see any obvious gamma rays coming from that. Okay, so it's one of three possibilities, this object. But it coincides with a faint smudge, for which we spent a lot of Keck time. And we have a trace, but with no lines. So we know the redshift of this galaxy is more than 1.5. Okay. So I don't think this is an orphan afterglow, because the orphan afterglows we find will all be very nearby, because they don't enjoy the Doppler boost that on one axis goes to give. So the two possibilities for this object is it's either a relativistic explosion, but whose initial Lorentz factor is not as high as GRB's, that is not like 100 to 1,000, but maybe 10. In which case the peak flux will come out maybe in soft X-rays or ultraviolet, depending exactly what this Lorentz factor is. And that would be an exciting possibility, because it would then show that there's a whole range of relativistic explosions out there, which have been missed by gamma burst detectors. The other one is, it is really a regular GRB, and for just reasons of satellite overlap and so on, there's a part of sky no satellite was looking at. So we are now looking for more of these things. But orphan afterglows, I'm not so sure that we are very sensitive. They are not so easy to find, in my opinion.
Just because of your flux limit?
Yeah, so we only go to about 21st magnitude. So if you ask the question, how many orphan afterglows would there be whose peak would be 21st magnitude, the volume we have is rather small. So I suspect orphan afterglows will probably, the best chance would be something like the dark energy canyon or certainly SST.
Is there a particular reason why you now include the Milky Way?
Yes, because before we couldn't process the data.
Oh, I understand, but wouldn't you expect to see the same thing?
Why are we doing the Milky Way? Oh, that's interesting. I thought it would be obvious. I'm doing the Milky Way and all that. Okay, but let's see. So you want me to like give an explanation, the scientific justification. Okay, so it's not enough if I just am curious about the Milky Way. Okay, well, let's see. Okay. So now, in order to make up the usual NSF proposal writing thing, the best way to approach that is to first drink, maybe a martini. That helps actually. So there are interesting things happening. There's been no regular patrol of the Milky Way for 100 years. So aren't you surprised that a nova went off in the Milky Way? It reached the peak magnitude of 2 meg, okay, and not reported by a single astronomer. Okay, well, so I think it's important that we not forget that our business is to go and understand phenomenology. So most astronomers may think novae are uninteresting, and they largely tend to be, in the sense that you don't go and learn anything immediately new. But for example, novae, it turns out they produce gamma rays. Okay, I think this is very interesting. I don't understand how, on the surface of a white dwarf with escape velocity of only a few thousand kilometers per second, I can actually accelerate particles to GeV energies. So if you don't keep up with this sort of curiosity-driven approach, you may miss the big picture. I know it's not a satisfactory answer, and definitely this answer would lead to a rejection of any proposal. And but I would simply say that I'm hopeful that if we do a systematic patrol of the Milky Way, the last time it was done was in Harvard astronomer was 100 years ago. It's hard to believe this. So we want to do a patrol of the Milky Way, a few times a year, and see what there is to be seen. And what if I find the first supernovae? I'll get like 6 Nature papers booked, and meanwhile you'll be struggling with your redshift 6.73 or
you say that it operates remotely inside the building. Do you need any people outside the building for aircraft spotting or space command?
No. Okay, that's a good point. We don't have anyone outside either. We can actually operate anywhere we want, including, we even have an iPhone interface now, if you wish. The reason is that we all operate in the ultraviolet. So in the UV, if you go below, I forget exactly where, at least in the US, you don't need Federal Aviation Authority permission. Because unless people are flying with their airplane windows open, UV is absorbed by glass. Okay, so that's why there's no restriction. On the other hand, if you do the same thing like as you do with MMT or perhaps an LBT for ground layer air in the visible, you do need all these permissions, and they become very It's fake only in the sense, yeah, so we have a camera that we have to give it some color. Okay, it's not red at all, it's 355 nanometers. We do need things with Space Command, but they're pretty flexible. They have come, they've been amused with our few hundred a night, so they give us some broad directives. It's not a big problem at all. I mean, that whole thing has been quite rapid.
Do you have any other questions? I mean, I always say with knowing what never to write in the NSF proposal to get your proposal through.